Well, I saw this question on YouTube. I have my methods to do it, and two methods. I think they're very, very good methods. So I would like to share with you. Now, here is the question: z plus 1 to the power of n is equal to the z to the power of n. Here, z is a complex number, of course. N is a natural number, positive integers. Now, I start with this, right? Move this one to the left. So it's z plus 1 over z to the power of n equal to 1, isn't it? Therefore, it's equal to z. So, so this one equal to 1 plus 1 over z to the power of n is equal to 1. And then 1 plus 1 over z is equal to nth root over 1. So nth root of 1. So nth root of a unit. So that is equal to what? Is equal to cosine theta plus I sine theta, right? Here theta is an angle, 2k pi over n. And k is equal to 0, 1, 2, 3, up to n minus 1. Well, namely that theta is an angle, 2 pi over n. See, I mean, evenly distributed over this unicircle. I love the unicircle. There are quite many applications in my videos. Now, because this is a unit, this is a root. One is a root of this. So start from this. Every 2k pi over n is the next root, and so on. So that you have n roots distributed over this unicircle. Their interval is 2 pi over n. Okay, that's what I meant here. So my 1 over z is equal to square root of n minus 1, which is equal to cosine theta plus I sine theta minus 1. Very good. So I can find a z. Z is just reciprocal of that one. So 1 over cosine theta plus I sine theta minus 1. So z is equal to cosine theta minus 1 plus I sine theta. Then I multiply by the conjugate, right? So z is equal to cosine theta minus 1 plus I sine theta multiply cosine theta minus 1 minus I sine theta under cosine theta minus 1 minus I. Okay, good. Now the denominator is equal to cosine minus 1 square, right? Plus I sine square. Yeah. And this is cosine theta minus 1 minus I sine theta. Yeah. So this one is equal to, this is a cosine square theta plus 1 minus 2 cosine theta plus sine square theta minus I sine theta. Here, this plus this is equal to 1. So it becomes 2 minus 2 cosine. So it becomes 2 minus 1 minus cosine. Right? And the cosine theta minus 1 minus I sine theta. This over that is a negative 1, negative half, right? Yeah. This over that, cancel with that is a negative. And minus half I and sine theta over 1 minus cosine theta. Yeah, good. Then z is equal to negative half minus I over 2. This is a cotangent, half theta. This is equal to cotangent, half theta. Now, then we substitute theta here, right? So this is minus half I cotangent half theta. Theta is this. So cancel 2 becomes n k pi. So I found the z. See? I think this is a very good method. Okay, but the only thing is that to modify is that cotangent cannot be 0. 0 is not defined for cotangent. Therefore, we we drop that k equal to 0. So k equal to 1, 2, 3, 4 until n minus 1. So that is so we have how many roots we have? We have n roots, right? N roots. It's true that here, when you expand this binomial, z to the power of n will be cancelled. So left over z minus 1, the highest power. So we have n minus 1's root. So it's true. We have n minus 1 roots. Okay, this is method 1. Now method 2. Well, it's these methods are great. Okay, the second method, z minus z plus 1 to the n is equal to z to the n. Method 2, I'll, I'll let z be r times cosine theta plus I sine theta. Here, r is the modulus, theta is the argument. There's no problem. Then, then this one move there, right? This one move there. You have a 1 plus 1 over z to the power n is equal to 1. And which means 1 plus 1 over z. 1 over z is a 1 over r times cosine theta minus I sine theta. Yeah, to the n is equal to 1. Yes, it's true. Well, it's obvious. Then we can conclude something because 1 is a complex number, the modulus is 1. Therefore, this complex number, the modulus must be equal to 1, too. So, which means that 1 plus r cosine theta square plus the 1 over r square sine square theta equal to 1. Okay, the modulus must be equal to 1. Then this one is equal to 1 plus 1 over r square cosine square x plus 2 over r cosine theta plus 1r square sine square theta is equal to 1. Yeah. Now 1 and 1 cancel out. This plus this one is equal to 1 over r square plus 2 over r cosine theta is equal to 0. Right? 1 cancel out. This plus this one is equal to 1 over r square. This is this. Therefore, from which we know that cosine theta is equal to negative 1 over 2r. Then we substitute this one over here. So z is equal to r times negative 1 over 2r. That's cosine theta, right? Plus I sine theta, which is equal to negative 1/2 plus r I sine theta. Wow. We know that z must be a complex number. The real part is negative 2 or negative half, which is a great. Okay, very good. Now, what then? Now then, we know that z must be a complex number on this vertical line, which is minus half, right? Minus half. So z must be there. Z must be on this line because the real part is negative half. And z could be, it could be there. And then, so let's pick up a 1 point to analyze. This is z. And this will be the argument, right? Theta. This is the argument for z. And this is minus half. Therefore, this one is r times sine theta. This is r, right? This angle is pi minus theta. Sine pi minus theta, sine theta is the same thing. So in other words, sine theta is sine pi minus theta. So this line is r times sine theta. This is half. So we can replace this part by tangent. So in other words, z is equal to negative half plus I. This is negative half times tangent, right? Negative half times tangent theta. Or positive half times tangent pi minus theta, which is the same thing. So in other words, we find the z is this, minus I over 2 tangent theta. Okay. All right. Well, now it's not finished yet because we haven't finished the imaginary part. Uh, Theta is this argument for z. Now let me draw a better picture, a big, big, big picture. This is imaginary axis. This is negative half. Okay, z must be there. If z is there, this is the argument for z, which is theta. And okay, this is z. Now, z plus 1 will be positive half minus half I times tangent theta. So this is positive half. They share with the same imaginary part. So this is z plus 1. Okay. This is the angle. This is the argument for z plus 1. This angle must be equal to pi minus theta, right? Because this is theta, so this angle is pi minus theta. Very good. So z is equal to negative half, huh? Minus. This is z plus 1. This is z. They share with the same imaginary part, but different in real parts. One is a negative half, this one is positive half. So theta is, see, look, this one, if I'm using this one, this is positive. So z plus 1 could be written as a positive tangent pi minus theta. If I'm using this angle, this will be positive, right? Positive half time this one. But eventually they are same. This is a negative tangent to theta. So therefore, this and that the same thing. They're eventually equal to the same thing. Now, here What is the theta? Theta is an argument for z. So theta cannot be more than half theta, right? Theta, the maximum is half pi, not half pi, not reach half pi. And then cannot be less than negative half pi. See, z could be here, z minus plus 1 could be there. The argument must be between half pi and negative positive. See, this is sorry, it's theta. I'm sorry, this is theta, not a z. Yeah? The argument for z must be between minus half pi to positive half pi. Okay. Now, something important here. We are given this is equal to this. What does this mean? What does this mean? It means that this complex number, the argument n times, is equal to this argument nth time. See, by the theorem of de Moivre theorem, right? The argument of this complex number times n is equal to this argument times n, right? Now, this argument, this complex argument is theta. This argument is this. Therefore, n times this is equal to n times this, pi minus theta. See, based on this, right? The argument must be equal, and it could be plus 2k pi, right? Because the period is 2 pi, so the angle could be plus multiple of 2 pi. And based on this, we can derive that theta is equal to 2n pi minus 2k pi. So theta is equal to half pi minus k pi over n. Wow. Then we substitute this one into what we have here. So z is this, minus half I tangent theta. See, that is this. And then we replace theta there is equal to negative half minus half I tangent half pi minus k pi over n. So this becomes negative half minus half. This is a cotangent, right? This becomes cotangent k pi over n. Wow. So we get the result. Now, k cannot be 0 because cotangent 0 is not defined. So k could be, look, we use this condition, okay? We can determine that k could be 1. When k equals 1, this angle is less than half pi. It's okay. 2, this angle is less than half pi. It's okay. 3, Okay, and until n minus 1, right? Yeah. So we get those n plus 1 minus 1. Yeah. So we get n minus 1 solutions. See, it's very good. Very good method. No, I haven't seen anybody did this method this way. So I would like to share I hope you like this one. It's a very good method. Thank you.